Noah Citron. I'm an engineer at A16Z Crypto. And today, we're going to be talking about the future of light clients. So before we talk about the future, let's talk a little bit about how light clients are going today. And the answer is it's pretty good. Ethereum has multiple light clients. By my count, Ethereum has no less than 7. And they make a wonderfully diverse set of choices. They're written in different programming languages. They have different dependency stacks. Some of them have different mechanisms for verifying Ethereum. And they even target different use cases, ranging from end-user verification to bridging. But we do have a problem, and that problem is that users are moving to L2s. And while this is not necessarily a problem itself, L2s are awesome. They're giving us cheap and plentiful block space. It is a problem because we have fewer options when it comes to L2 light clients. But we would like to change that. So before we go into how we're going to change that, we need to sort of understand what a light client is and how do they work. So first, what's a light client? Well, a light client is a piece of software that gives us higher confidence in what data on Ethereum is. It might not give us as high confidence as, say, running a full node, but the thing that light clients give you is they are very easy to run. You can even run them on your phones, in the browser, or really anywhere you can imagine. They're very, very lightweight. But now let's talk a little bit about how light clients work. So I have kind of a diagram here, and it describes like a typical light client. Not all light clients might break up components in this way, but this is kind of a good model for us to start with. So as you can see, the light client splits itself into a consensus layer and an execution layer. This is kind of typical in all sorts of clients, whether it's a light client or a full node. And the consensus layer's job is conceptually very simple. The consensus layer's job is to figure out what is the block header and then send it off to the execution layer. Now, it's conceptually simple, but in practice, quite difficult. Now, the executions layer's job is to actually do something useful with those block headers. I don't think I remember a time a user has ever asked, hey, give me the block header. That's not really particularly useful information, but there's a bunch of useful information that can be inferred from the block headers. So the execution layer's job, or some people call it the execution prover, its job is to actually infer interesting information and ask and answer questions of the user. So let's go through a quick example. In this case, it's me, a user, who wants to know my ETH balance. So I sort of send over to the light client like, hey, what's my ETH balance? What's the balance of ncitron.eth? And it goes in the execution layer. And the execution layer says, well, I don't have Noah's ETH balance. But what it does have is the block header. And what is inside of the many things in a block header, there's the state root. And what the state root is it's the Merkle root of the entire tree of all state on Ethereum. And what's great about these Merkle trees is they're a sort of authenticated data structure, which means that we get to be able to generate proofs about what's inside of them. So the execution layer can ask some untrusted data source, hey, give me a proof of what Noah's balance is. It can verify that proof. And then it figured out I really have 1 ETH. And it can send me back the answer. And now I know exactly how much ETH I have. It turns out you can do this sort of strategy for a bunch of things. If you want to know your receipts, there's a receipt root, so you can prove receipt inclusion. If you want to know a transaction, there's a transactions root. We can even sort of simulate ETH calls by running a local EVM and fetching state using proofs as needed. But we've kind of viewed this consensus layer portion as a black box. It just verifies headers. But how does this work? So on Ethereum at layer 1, we use the Altair Light Client Sync protocol. And this uses the trust in the Ethereum validators signing block headers. So the way this tends to work is that Ethereum has this thing called the Sync Committee, which is a set of 512 validators that are elected for a 27-hour period to just sign blocks. And if you know who the sync committees are, you can see their signature and kind of have a good understanding of what's happening on Ethereum. And then there's a little bit of machinery on how do you update your sync committee every 27 hours, but we'll skip that. But now let's go to the L2. How will an L2 light client consensus layer work? Well, the validators can't help us. L2s don't have validators. They use Ethereum. And the Ethereum validators don't necessarily have particularly good understanding of what's happening in an L2, which means we need to figure out something new. And that's pretty much what we're going to be talking about today. So before we kind of go into, OK, how do we build these L2 consensus layers, or L2 light client consensus layers, we need a model of L2s. So in our model of L2s, we're going to sort of think about blocks. And a block has two kind of components. It has block inputs and block outputs. We can view these as like the inputs to the state transition function and then the outputs that are derived from running the state transition function. And generally, the block inputs are the transactions. And the block outputs are things like the state route, the receipt routes, the transactions route. These are things that normally go in the block header. So we think of a rollup being a thing that puts its L2 block inputs inside of Ethereum blob data, and Ethereum blob data's job is to sort of make sure that once it's in there, it stays and it doesn't get sort of reordered. And then we have our L2 block outputs, which are really our block headers. And in a rollup, we generally have these bridges, and the bridge's job is to use some system, either a snark, a dispute game, or something else, and to derive the block outputs, the block headers, from the inputs. So for our purposes, we're going to make this model a little bit more generic. And we're going to replace sort of Ethereum with an Irreversibility gadget and these snarks with a Validity gadget. Now, let's quickly define these. So an Irreversibility gadget convinces a verifier about what the L2 block input data is. And a Validity gadget convinces a verifier about what the L2 block output data is given a given L2 block input. Example of an Irreversibility gadget is the data posted to Ethereum and checking it via the existing Ethereum light client. And an example of a Validity gadget is a snark that implements a state transition function. So once we have these gadgets, we can actually implement sort of a generic view of an L2 light client. And in this example here, we have the light client and the Irreversibility gadget and the Validity gadget. The light client starts by saying, hey, Irreversibility gadget, convince me what the block inputs are. And it receives the block inputs, a proof, it checks the proof, and now it knows the inputs. So next it talks to Validity gadget, says, hey, Validity gadget, convince me of what the block outputs are. And it sends the Validity gadget, sort of figures out the block outputs, generates a proof, and sends it over. The light client verifies it, and now we know the block outputs, the block headers, and we've kind of done our job. So to understand the security of this, really the security of breaking our light client is the security, or the minimum of the security of our Irreversibility gadget and our Validity gadget. But let's now instantiate a light client. So to instantiate it, we're going to use, for our Irreversibility gadget, the Ethereum alter light client. So we're going to sync a light client and read data off of Ethereum. And now we know the block inputs. For our Validity gadget, we're going to use a snark. It can potentially be a snark implemented by the bridge. And now when we execute a snark, we have an L2 light client. But we have one big problem here, and that problem is latency. So rollups tend to post data to L1 only every couple minutes. And on top of it, it takes some extra time to finalize. And snark generation today is slow. Hopefully in the future it won't be. But this means that our light client runs way too far behind the tip of the chain. So what are we going to do about that? Well, we are going to invoke the light client superpower. And the light client superpower is to balance security with latency and performance. So now we need to do something. We need to choose Irreversibility gadgets and Validity gadgets that offer lesser security guarantees, but lower latency and higher performance. And when we do this, it means that we can pick any Irreversibility gadget and any Validity gadget that we can come up with. And we have an L2 light client, and we can make these choices so that they are best for a given use case. OK, so now we're going to talk about some Irreversibility gadgets. These gadgets are kind of hard, because the L2s need to implement them themselves. Because right now, the sequencers have the full right to decide what gets put on Ethereum, and we can't force them to do anything. But the L2s can build mechanisms that will force them to commit to what they're going to put on Ethereum earlier. So we've already talked about Ethereum finality as a Irreversibility gadget, but we also have three others that we're going to discuss. So the first one's very simple. It's a sequencer commitment. What this is we have the sequencer receives the block's inputs. It might just be generating the block inputs itself. And it's going to sign them. And then once it signs the block inputs, it sends them off to the light client, and the light client assumes that they're valid. And that's it. Light client just trusts the sequencer. It's not a very good, but it's a good start. It's a good first start. So our latency is very low. Really, the only hot path we have is signing. But our security is also very low. It's just as secure as trusting the sequencer. What's nice about this design is that most L2s already implement this today as part of their sequencer pre-confirmations. So we kind of get it for free. Now, I think we can do a little bit better. And we can add some economics to this. We can bond the sequencer to their responses. So in this case, it's kind of the same as before, but we have the sequencer start by bonding some assets on L1. And then they act kind of the same. They sign block inputs and send it off to light clients, and the light clients accept that it's valid. Additionally, the light client might want to run an L1 light client to sort of check up on the bond and say, is the bond big enough? And we add sort of an extra entity here, which is the watchers. Watchers are just sort of a group masquerading as light clients, and they also ask the sequencer to sign block inputs. But what they're doing is they also are running full nodes, and they are trying to figure out, is the sequencer being honest, right? They're going to watch L1 and see, is the sequencer actually going to post the data on L1 that they say that they're going to post? And if they don't, they sort of present previously signed inputs that conflict with what the sequencer put on L1, and it will slash the sequencer. So this is much better. The latency is still very good. Our hot path is just signing. And the security is better, and we could scale it kind of as much as we want just by increasing the bond. So let's go a little bit further and talk about one last irreversibility gadget, which is a fast finality committee. Now in this model, we have the sequencer sending block inputs off to a committee of n nodes. And what this committee's job is to agree on what the sequencer said. So it does a little bit of consensus, and it generates something called a quorum certificate, which is essentially a little proof that they did consensus correctly. And then they send a quorum certificate off to the light client. The light client verifies that the fast finality committee really agreed on what the sequencer said. And if it did, the light client accepts the inputs as valid. Now, we also have to make one change kind of to how the rollups post their data to Ethereum. And it's that you change kind of the validity of the rollup validity rules to say that some block inputs are only valid if they come with a quorum certificate that the fast finality committee sought. And now for latency, it's still pretty good. We know how to build relatively fast consensus mechanisms as long as n is not too big. And for security, it's reasonable, right? It turns out that we can even scale our security. So right now the security is that as long as at least or less than 1/3 are malicious, we should be good. But we can also add sort of bonds to the system and ensure that the fast finality committee is staked. And if they act maliciously, we can submit evidence to this onto L1 and slash them. And what's really cool about this is that there are sort of some traditional issues with slashing a consensus or operators of a consensus mechanism when more than 2/3 are malicious. But since we can do the slashing on Ethereum L1, we get around that completely, and we are able to tolerate greater than even 2/3 malicious and still slash them, even though the light client will be deceived. So OK, that's our irreversibility gadgets. So now we have a sort of good set of options for how do we figure out what the block inputs are, at least how do we figure it out faster than just waiting for it to land on Ethereum. But we need a couple of mechanisms to talk about how, given those inputs, how do we know the outputs? So we've already talked about snarks, but we have kind of 4 other ideas for what we could do. And the first one is sequencer commitments. This is basically the same as what we talked about in the sequencer commitment version of the irreversibility gadget. But in this, rather, the sequencer sort of receives some block inputs. It executes them. And then only once it's executed, it signs the input, comma, header tuple, and then sends that signed tuple over to the light client. The light client checks that it is the inputs it expects, and then trusts the headers as valid. Now for latency, still very good. The hot path is really just signing. We will probably execute eagerly, so we don't actually have to wait for that. And the security, though, much like before, is not so good. What's nice about it, though, is like before, sequencer pre-confirmations implemented by most L2s today give us this for free. But we can do better. We can do sort of the same strategy we did before. Let's add economics into the situation. So in this, we can have a bonder who bonds on L1. And in this case, the bonder doesn't need to be a sequencer. It can be anyone. And the light client will send over some block inputs that it had received from its irreversibility gadget and ask the bonder to execute it. They execute it, derive the block headers, and then send sort of a signed input header tuple. And then when the light client sees it, they just accept it as valid. Now again, we have watchers. The watchers are either masquerading as light clients or maybe just receiving these tuples from the light clients themselves. And they run full nodes. And if they notice that what the bonder is saying the output is different than what they see it as, they will generate a snark that executes the inputs and proves that it's not the same block header. Now, this snark can be executed slowly. We don't have to worry about doing this very quickly. It can maybe take a day to generate. It doesn't matter. We just need to be able to eventually generate it, and then we can present this snark as well as the bond or signature that shows it's different, and slash the sequencer. So latency of this, again, still very good. The hot path is just signing. And the security of it is also OK, because we can scale the security as high as we want by just increasing the bond. You can even imagine asking for many bonders what their position is. And now you can kind of aggregate the security through multiple people rather than just requiring only the sequencer to be able to bond. But I think there are some other interesting sort of parts of the design space. So next we're going to talk about just using TEs. So in this case, it's really simple. The light client sends over the block inputs, TE executes them, and then signs them. But the one additional thing they do is they send TE attestation. TE attestation is a special thing that a TE can do to kind of convince someone what kind of code is running on it. And the light client sort of receives the signature, checks that it's valid, receives the attestation, checks that the TE really is running the code they say they're running. They're hopefully running the code that executes the state transition function. And then it accepts it as valid. The latency of this is very good. The security of it, we don't know. Lots of people have opinions on how secure TEs are. But what my belief is that however secure TEs are today, they're certainly going to get more secure in the future, which means that this is maybe a good part of the design space. And we're going to talk about one final validity gadget. This one is actually my favorite. So this is off-chain dispute games. So an off-chain dispute game is going to function a lot like a traditional dispute game that we see optimistic rollups do, with the one major difference being that an optimistic rollup does its dispute game through the layer 1. So you have all of these players who are arguing about what the output is, and they play their moves on an L1 smart contract. And the problem with this is that you have to assume worst-case inclusion times for every move in the game, which means it plays extremely slowly. Most dispute games take at least a week or have a week-long window to be played when you're playing it through L1. Now, what's cool about an off-chain dispute game is that for our light client, we can simply connect to multiple servers. We have no idea how many of them are malicious. Even the majority can be malicious. We're hoping just one is honest. And we can have them send us, hey, what's the block header given these inputs? They all send over the block header, and if they all agree, you say, perfect, life is good, we're going to accept it. Now, if one or more disagree, we make them play a dispute game, but we make them play a dispute game not on L1, we make them play a dispute game through the light client. All the moves get played in the light client. Now, the light client certainly doesn't want to censor the players, so we have relatively good guarantees that all of these players are able to make their moves in a timely fashion, which means we can run the game very, very quickly. So the latency of this is OK. If we assume the happy case that they all agree, the latency is fast. If we assume the case that a dispute's going to happen, the latency is less fast. Even though we don't have this horrible latency that a on-chain dispute game has, we still have a little bit of latency because each of these players do need to do a lot of computations. But modern kind of dispute game provers are getting better and better at doing this. And for security, I think it's really fantastic because we have what's called existential honesty, which means as long as you're connected to just one honest player, you're guaranteed to get the correct output. Now, another thing that's good about this design is once we identify sort of the set of players we're connected to that are bad, we pick maybe 10, 20 people to connect to, hopefully some people with maybe some reputation. And the second we see one has lost a dispute game, well, we kick them out. We never ask them again. So it means that we can use this mechanism to keep a kind of set of very reasonable players to work with. So now with these irreversibility gadgets and validity gadgets done, we get this really nice light client security latency trade-off matrix for L2s. So we have all of these irreversibility gadgets and all of these validity gadgets, and you get to pick one from each and design a light client that works for your use case. So to recap, we have a new way of thinking about L2 light clients. And to build better L2 light clients, we just need better irreversibility gadgets and better validity gadgets. So what are we doing with Helios? We want to implement all the L2s and all the gadgets. So Helios now supports the OP stack, uses sequencer commitments for both irreversibility and validity. And what's next? We're going to add more L2s, more validity gadgets, and more reversibility gadgets. So if you want to help, reach out to me on Telegram. Here's my Telegram here. We'd love to help work together and build the future of light clients. Thank you.
All right. Thank you so much, Noah. We have some very sophisticated questions here. I'm happy to go through them and ask you. So what incentives have regular nodes for serving all these light nodes? Right now, they are minorities, so this doesn't matter. But what happens when light nodes start to flooding normal nodes?
Yes, that's an awesome question. So there are kind of a bunch of different designs for how a light client gets data. And sort of the two popular ones are, one, a peer-to-peer network. A good example is the Portal network, who's doing great work. And in this case, it's kind of hard, right? You're hoping they sort of altruistically serve data. And maybe that works, maybe that doesn't. We'll have to see. But there are other options, right? An option that Helios uses, and Helios is the light client I work on, is we sort of implement the RPC proxy architecture where we connect directly to a traditional RPC, and we use that to fetch the data we need, but we do it in a very special way. We're using lots of eth_getProof calls. And this means we have light clients have a direct business relationship with who they're getting data from, but they don't have to trust that person. They just need to make sure that person actually responds to them. So we do have kind of a bit of a spectrum here, and hopefully the peer-to-peer network stuff works. I really, really hope that we can do it that way. But we also have these RPC proxy designs.
OK, thank you so much. Then is there any small protocol changes rollups could do to improve the trade-off between security and latency for rollup light clients?
Yes, great question. So for validity gadgets, we can just make them as we see fit. We can spin up TEs, we can bond. But for irreversible gadgets, it's much harder. This is because while the sequencer hasn't posted the data back to L1, we have no good way of knowing what they'll post. We just have to hope they tell us the truth. So L2 teams, it would be awesome if they think about building these sort of fast finality committees or start bonding to what they say they're going to post. And if we do that, we end up in a very, very nice world because we have more we can work with. Additionally, there are some changes that L1 could do. We heard Justin talk about the beam chain, which includes fast finality and lower slot times. And if we have fast finality and lower slot times, we can do techniques like based sequencing and just have the L2s post their batches every block. And in this world, we get basically the most secure possible irreversibility gadget, Ethereum, with low latency, which I think is probably the end game, but it's going to be a little while.
All right. Next question. I have different ones. What would be the economic incentive for a bonder?
Yeah, it's a little weird, right? Because if you bond, once you sort of sign a message, I can't prevent someone from forwarding that message off. So it's like this data market problem where it's hard to keep that signed message secure or hidden later. So it's very hard to make it so that you pay for the bond. There may be sort of these insurance-style designs where when the bonder gets slashed, maybe half of their assets are burned, but the other half can be given to the wronged parties. And in that case, the wrong party is one of these light clients, and they could pay directly for it. And then in this case, we actually have kind of a direct relationship where the light client is paying not just for the signed message, but really for the insurance when something goes wrong. And this gives them a relatively nice economic design.
OK, and this one is nice. When we achieve stateless clients on Ethereum, will light clients become obsolete, assuming 99.99% internet uptime in the future?
No, light clients become better. So there are two types of stateless clients, I guess. One is a stateless executing client where we can just execute all of the transactions locally, but they have witnesses to all the state that they touch. And doing that is still going to be hard. You're not going to be able to do it on a phone or on other potentially really lightweight hardware. So we'll still need light clients. Now in this future Beam world where we've snarked everything, we still need light clients because the consensus layer is very simple. The consensus layer is grab the proof and verify it, which would be awesome. I hope we do that. But we still need to build these execution provers. We still need to have strategies for how to fetch data and sort of coordinate all those proofs. So we'll absolutely still need light clients, and I think stateless clients are going to make light clients even better.
All right.